Our speaker tonight is Dr. Cynthia Breazeal, and she's visiting us from the Massachusetts Institute of Technology, where she's director of the Personal Robotics Group at the Media Lab there. We're very grateful for Cynthia for travelling on a whistle-stop tour. She arrived yesterday on a plane and she's going out tomorrow, so she's maybe a little bit tired. And thank you very much. We're delighted to have such an honourable speaker, and we're looking forward to the talk. Also, this evening, our Master of Ceremonies here is Derek Mooney, and Derek will be, firstly, he will introduce Cynthia and give us some more information on her profile and background. He'll also be conducting a Q&A session, which we'll have after Cynthia's presentation. Derek, as you know, is one of Ireland's best-known presenters, TV presenters, and he is a prolific broadcaster, particularly in the area of natural history, and has worked on shows such as Habitats, The Nature Line, Nature Trails for RTE Radio 1, and is also involved in the very popular Winning Streak TV show. And maybe if we play our cards right, he might actually give us a ticket on the show, a chance for the show, any chance. I keep my fingers crossed. So thanks again very much. You're all very welcome, and I'll introduce you to Derek. Thank you.
Appreciate it. Thanks very much indeed. Well, good evening, everybody. My name is Derek Mooney, as Una has said. I'm a broadcaster, producer, and presenter with RTE Radio here in Dublin. For those of you who are not from Ireland, RTE is Ireland's national broadcasting service. And I present a daily programme on Radio 1 called Mooney, which is a magazine programme. It's a mixed bag of everything and anything. And today we had the pleasure of having Cynthia on talking about robots. And I have to say, by the time she left, I actually was convinced I was going to end up marrying a robot. I thought, civil marriages, what next? Because she managed to convince me that in time, robots will have emotions and feelings, and they'll even have a sixth sense. You can make your own decisions on that. But to formally introduce Cynthia, Dr. Cynthia Breazeal is an Associate Professor of Media Arts and Sciences at the Massachusetts Institute of Technology, where she founded and directs the Personal Robots Group at the Media Lab. She's a pioneer of social robotics and human-robot interaction. Her research program focuses on developing personal robots that interact with humans in human-centric terms, work with humans as partners, and learn from people via tutelage. She is author of the book Designing Sociable Robots. Tonight the talk is titled The Personal Side of Social Robots. Will you please welcome Dr. Cynthia Breazeal.
Good evening. It's a pleasure to be here and to participate in Science Week. Thank you for the introduction. So I am going to talk to you about social robots, and clearly a lot of the real-world applications for this work concerns bringing robots into the everyday lives of real people, not necessarily just the specialists and so forth. But to set the stage, I'm often asked, how did I get started in this field? And I think, as perhaps many of you who may have decided to pursue careers in science and engineering, for me, it started when I was a 10-year-old little girl, and I saw Star Wars, and I fell in love with these robots. And I think the thing that was so captivating to me about the droids, these two droids, was not that they were only, of course, incredibly capable and intelligent in their interactions. And of course, throughout the movies, there's many instances of them getting their human counterparts out of various predicaments. But, these robots were full-fledged characters in their own right. They had personalities, they had emotions, they had a relationship with one another, they had relationships with the humans that they interacted with. They were more like friends than just tools that people used. And, we cared about them and they cared about us. And I think, as an impressionable 10-year-old kid, I saw that. And of course, if you look at the work that I do, had this sort of indelible impression on how I aspire to what robots could be in the future. It was a sort of a vision that was seared in my 10-year-old consciousness that I've carried with me today. So, but then you might ask, so where are all the robot sidekicks? We all fell in love with these robots and so forth. Where are they today? And of course, we're entering a really exciting time in robotics, in that for a long time people saying the robots are coming, they're coming. It's like, where are they? They've been in factories and so forth. You've seen them now go, into the depths of the oceans and off the planets and exploration. And it's like, in many ways, I think the final frontier is your living room. And the reason why is, if you think about it, our society, our interactions, It's much more complex, much richer, much more diverse than a robot that's navigating, say, in an inanimate world. And many of the research challenges that I'm trying to tackle and I'm going to share with you today really has to do with bringing robots into the everyday human environments that we take for granted but are incredibly rich and incredibly complex and incredibly dynamic. So this is just a Scientific American cover where Bill Gates, even wrote an article on the dawn of robots comparing this sort of nascent robotics, personal robotics industry to where personal computer industry was in the 1970s. So, a lot of people anticipate that this is going to grow and become very big. And I think we're at, again, this very sort of significant time, and I think we're just at the threshold between the first personal robots we see today in terms of toys and vacuum cleaners and so forth to what they could be in the years to come. So robotics as a field, if you think about it, the 40, 50-year history, really a lot of the work is focused on robots that are capable in their interactions with things. So objects that are governed by the laws of physics. And through that, you see many applications and a lot of research efforts in doing just that. So I mentioned planetary exploration, the ability to navigate these sort of inanimate worlds, manufacturing, where you're, again, using tools to perform this sort of repetitive task again and again. And now you're starting to see these highly dexterous robots. But fundamentally, this is about robots interacting with things. And, of course, the new challenge is what robotics will be about, if you talk about personal robots, is interacting with people to do things. And this is a fundamental different set of questions that raise, because it's really about trying to understand, building robots that can interact with entities that have minds, namely you or animals. And the fact that our behavior is governed by having mind means that there's a whole different set of ways of thinking and understanding that these robots, I think, are going to need in order to really interact with us in the rich way, in a capable way, that is going to be required for their acceptance and functionality. So, today, if you look at, top research labs such as NASA Johnson Space Center, you see examples here of, this is Robonaut. Robonaut is a humanoid robot who's designed to work as a teammate for astronauts. And the idea here is that the robot can use the same tools as the human astronauts do when fully suited, so you don't have to retrofit space shuttles and so forth in order to have Robonaut interact with people. Now, robot, of course, doesn't need oxygen, can operate on the outside of the space stations for a much longer period of time. So the question here is, in this highly trained sort of situation, the robot is actually interacting with the person much more like a partner or a teammate rather than as a tool that's operated. And of course, I don't know how many of you have seen this advertisement. This is obviously from Honda, portraying this sort of vision of the robot in the home. And I get a kick out of this picture because, first of all, it's a family portrait, basically. And, the dog, Fido's been kicked to the curb. He's still part of the family. But, there's kind of like some status here that suggests in the fact that, Osmo was here with the family. Poor Fido was down here. But clearly these images are starting to come to us not only through science fiction, but from advertising from real companies. So, again, this is a very, exciting time. So a lot of this work is then... it's just informed and just appreciates the fact that we as humans were profoundly social. And when we bring these robots into the environment, we find that our ways of trying to think about them, understand them, is also profoundly social. So, even in the case of something like the Roomba, which is just this sort of disc that vacuums your floors, it sends off these anonymity cues. And this is in 1946, there was a set of psychological experiments showing that even simple moving shapes on the screen, if you show these to people and ask them to describe what's going on, they don't describe it in terms of vectors and spatial relationships. They talk about the mental states of these shapes, that the little triangle is scared of the big triangle and is defending the circle and they're escaping, So again, this is just appreciating that the social intelligence is a fundamental way we have of understanding and thinking about the world. And when entities, even if abstracted these shapes, push those buttons, we can't help but unleash this way of thinking about it. So perhaps it's not surprising then that people anthropomorphize even things like the Roomba, so making these sort of tea cozies with eyes, and kind of, anthropomorphizing them. Or I like this little, I don't know who did this, but this all work and no play makes Roomba a dull toy, This sort of playfulness that I think, is another aspect of the appeal of these kinds of systems, is it's fun, it's whimsical, it's fun, it's playful, and my hope is that these robots are not just going to be these drudging sort of things that are useful, but that we really enjoy them. they put a smile on our face as well. I think that's something we don't want to neglect. So, then the implication there is perhaps personal robots are going to also have to be profoundly social in the way that they have also this social intelligence, this way of thinking about and understanding us as part of the social world. So I'm going to present a variety of research that we've been doing to try to crack that nut. And again, these are fundamentally new questions in robotics, questions that we've never posed before, because we haven't really thought seriously about robots in the context of everyday people. So I'm going to be talking today then about robots that are really designed, not only to sort of recognize patterns of activities and actions and what you're doing, but to actually try to relate to you. And I'm going to talk about that in a little more concrete, but actually try to coordinate their internal states, which you might, think of akin to things like beliefs, intent, desires, your sort of mental, psychological states, and coordinate those states with your mental states in order to work as partners, to do things together, to do joint actions together. And in doing that, in psychology, this term is called theory of mind, or sometimes it's called mind reading. It's not about ESP. It's really about the way that as we watch each other move around, we don't have to say a word, but we understand the internal states, the motivations and goals that are going through your head in order to allow us to predict and understand your actions. And I think a challenge of social robots is to essentially endow them this sort of theory of other mind competence. And in humans, this social cognitive ability underlies our whole suite of social behaviors, from communication to many forms of social learning such as tutelage to collaborative teamwork, our ability just to coordinate ourselves in partnership. This social intelligence is fundamental. So to highlight a variety of aspects of this work, I'm going to talk to 4 different themes. So the first, again, is this idea of social intelligence. The second one, I'm going to talk a little bit about these robots, in this case, Leonardo robot, that's able to learn from human tutelage, to learn from natural human interactions with people in the way that people are naturally inclined to teach. So rather than expecting humans to learn new interfaces and new ways of communicating and interacting, how do you build robots that just understand our behavior, that we can just be us, and they can learn from that? Then I'm going to start talking a little bit about the actual social affordances of robots. So you talk about, say, socially influencing behavior. We know from human social psychology these nonverbal cues like interpersonal distance, eye contact, facial expressions, gestures, postural mirroring, all have a very important and often subconscious effect on how you perceive other people in terms of how trustworthy you see them, how persuasive, how much you like them. And it turns out that if robots exhibit these same behavioral patterns, you make the same kinds of inferences. So a robot, simply by the way it makes eye contact with you, can impact how trustworthy you perceive it to be. And that has interesting implications and possible applications that we might have not imagined 10 years ago. And then I'm going to end pushing on that theme with just communication and thinking about, robots are these embodied systems that share these novel cues. Maybe one killer application of robotics in the future is just as a new kind of communication medium in its own right to facilitate human-human communication across distance, but embodied through a physical artifact rather than just a cell phone or Skype or so forth. So just kind of taking all of that to the next level. So the first thing I'm going to highlight then is the social intelligence, the social way of thinking and understanding. And a lot of this work, this is my middle child, Nathan, when he was just a baby. Much of this work is actually heavily inspired and guided by insights from developmental psychology. And, if you think about people, we are tremendously socially complex and sophisticated. It takes us years to develop that competence. The thought of being able just to program those types of skills and understanding in a machine is daunting, if not impossible. So early on, I thought maybe one way to grapple with this question is to look at developmental psychology, social development, to have the robot acquire these abilities and these ways of understanding through interacting with people. So the challenge, in some sense, was to build a sort of robot-like infant, where people played the role of caregivers to try to bootstrap that kind of intelligence. So you're going to see a variety of works that really look at a diverse range of literature and development psychology and try to glean lessons and principles that can be used to bootstrap the social intelligence of robots. And one of the key insights, if you look to developmental psychology, is just the appreciation of, infants, we're human, they're anthropomorphic. So being in a body with a mind in a world with like bodies, with like minds, yields a lot of multimodal associations between the self and the appearance of other agents, between the behaviors and events and times of the self and the behaviors in other agents, and based on those correlations, your ability to start inferring the internal workings, the states of mind of the self and the other agent. So basically using yourself as a simulator to be able to take the other's perspective as a way or a mechanism or strategy we have of understanding others, and how can you put that way of thinking and understanding into a robot. So the first story I want to tell looks at one of the earliest forms of social learning and interaction that human infants exhibit, which is imitation, in particular early facial imitation. And scientifically, this is a really intriguing question because, infants, as much as just, hours or even minutes old, can imitate in simple ways the expressions of adults. And so how can you do this? Because if you think about the problem, you're a newborn infant, you can see something like somebody stick out their tongue, a sort of like facial gesture, facial expression, and that's a visual stimulus. But then you do a motor response, so it's a cross-modal association. So the question is, how do they do that? Because they haven't seen mirrors of themselves. How do they make this cross-modal association? And one of the influential thinkers, developmental psychologists in this area, is Andrew Meltzoff, and he and Andrew Meltzoff and Moore proposed what's called the AIM model, active intramodal mapping hypothesis, by which this is sort of the substrate that infants come into the world with that allow them to do this basic form of imitation. That, of course, if you look at imitation in infants, it goes through a very rich, very sophisticated developmental trajectory in its own right. But looking just at facial imitation, the idea here is that, infants are born into the world with a basic motor repertoire, and they babble. They can basically kind of go through this little repertoire, and they don't necessarily have meaning behind it. They're just exercising their motor systems. But once you put the infant in front of a parent or a caregiver or another person, we are prolific imitators of infants. We are prolific imitators of others that we're trying to form that connection to. So the idea is, it's not as if infants come into the world right off the bat necessarily being really sophisticated imitators, but it's the fact that our parents imitate us, that we learn these correlations and learn, maybe we start off with a rough mapping of eyes kind of map to eyes and mouth kind of mouse to mouth, but through these interactions of having adults mimic us, we gather these associations and can start learning the mapping between, if I move my mouth in this particular way, it becomes more nuanced and subtle that I can map that now to you. And then eventually I can flip the tables and do that imitation back at you. So I'm going to show you a video of a computational model of that we did on this is a simulation actually, of just training the mouth region of our Leonardo robot. So these are the basic repertoire of the 4 mouth poses. And the idea here, again, is Leo's playing the role of the infant. He's motor babbling. He's just going through this repertoire of facial movements of the mouth here. And the human is actually imitating that, So the human's playing the role of the parent. And then based on that, so we have a vision system that's tracking the facial features of the person. The robot is sensing the contingency between which region the human is moving to which region it's moving in order to basically gather this training set of samples of when I move my mouth in this way, this is what I see. And then it uses a neural network to basically train up what's called an intramodal mapping. So this thing here is basically what Meltzoff proposes is called an intramodal mapping that goes from the visual coordinates of what you see on a face to a re-representation of that within the motor coordinates of the imitator. So this representation is actually in the motor coordinates of the robot that then it can do a basic match, sample to match process. So based on the repertoire of basis postures, you can find a weighted blend of those postures to approximate the intramodal representation. So it's a search to match process, basically, in order to do the imitation. And this is what you would see in the observable world. This is essentially a depiction of the internal representation in the motor coordinates. And then based on that, you can even have the trained model imitate novel facial expressions. So this is the idea here, is that the robot is basically modeling the sort of key principles and insights for maybe, any theories, can be debated, but maybe how infants actually do this. So from this simple interaction, if you extrapolate that, you can think about these intramodal representations as being these sort of mirror neuron-like processes. The motor knowledge of the robot in this case can be used not only to produce these actions, but also to help it recognize these actions in others. And the way it learned these mappings is through imitation, and so it's learning this sort of body mapping. How does my body map onto your body? And if you have that ability to mimic, this now is a way of interacting and learning that can bootstrap now more sophisticated and other forms of social learning. So another example then could be something like social referencing. So social referencing, if you look at babies, it starts to peak right around sort of 1 year of age. So it relies on a number of precursors, the ability to share attention, the ability to do this sort of imitation. But social referencing, you do this as adults too. You encounter a sort of novel situation, you don't really know, is this thing good or bad? What should my attitude towards this thing be? And so you often look to your trusted friend, or if you're in the case of a child, you might look to your parent. And you look at their assessment. And if they're acting encouraging and so forth, you might go, oh, maybe this is okay. And if they're looking fearful, then maybe you'll back off. So in the classic set of psychological experiments, this is called the, oops, did I just turn that off? I think I just turned off the projector. I meant the laser pointer. Can you? Yellow button. Yellow button. Anyway, so this is a visual cliff experiment. So the idea is for these roughly 1-year-old infants, they have this sort of checkered pin where there's actually a drop-off, but there's a glass over it. So if the infant actually walks across, they're not going to fall over. But they have the appearance then of a visual cliff. And this is at an age where infants, they're not really quite sure what's safe and what's not safe. So as the infant approaches the visual cliff, the experiment then is to have mom on the other side either saying, come on, it's okay, to have the infant kind of learn, oh, maybe this is an okay situation to walk across, or to go, don't do it, and so the infant will back off. So that's social referencing. That's kind of the classic psychological experiment that people have looked at for infants to see at what age infants are able to do this sort of learning. Is it going to come up?
It takes a couple minutes.
All right, I'll just keep talking. So I'm going to wave my hands through this. So we've talked about imitation. We've talked about this basic pathway by which the robot can play the role of the infant and do this motor babbling. You see those interactions. You imitate it. That's the way in which the robot starts to learn the mapping in which it can actually mimic you. So that's kind of the first step of the process. Now, it turns out that in other psychological experiments, there's a lot of dual loops between motor response and motor emotional response and internal affective states. So even if you look at, say, college students, it turns out that even just the act of putting your face in a particular configuration, like a smile or a frown, can induce the corresponding internal affect. So if you smile, you tend to feel more positive. If you frown, you tend to be more negative. So one mechanism potentially by which infants may learn how to do the social referencing is given this imitative interaction. I see you smile, I mimic that can perhaps induce a positive affective state within the infant. So then it can start to learn correlations between I see your smile and I feel more positive. And then to learn the loop between now I don't have to actually explicitly have to do the facial expression, now I just see you, and that induces an affective state within myself. So this is a strategy that Leonardo has been modeling, we've been modeling within Leonardo's sort of empathetic experiential way of trying to coordinate its internal affective states with that of the person that it's watching. And then, once you can do that, then you can do this, again, this is the point, the direct connection between you see the facial expression and you respond to it. So I'm going to show a video then, are we up now, of the social referencing interaction with Leonardo. Leonardo now has the fur on, so we can show the robot. And I don't know if you guys know the Sesame Street characters.
Leo, this is Big Bird.
But this is a novel thing. Leo's never seen it.
Can you find Big Bird?
Clearly, Leo has some basic speech recognition. This is basically to show that he can see Big Bird. He can associate the name Big Bird with it, and he's verifying that you can see it.
Look at Big Bird. Look at Big Bird, Leo.
Now, Maddie is giving you an attitude. He's
Leo,
acting,
look at Big Bird.
speaking
Isn't he
in
cool?
a very positive tone of voice. His facial expressions are very positive.
Hey, Leo, look at Big Bird.
And Leo is doing this sort of empathetic mechanism by which it's inducing a positive affective state within itself.
Look at him, he's all yellow and fluffy.
Sharing attention with Maddie, so understanding that his reaction
Leo,
is
look at
about
Big Bird.
this thing, and starting to form an affective tag, essentially, of positive effect with this novel stimulus called Big Bird, that's this yellow thing. And now he's picked up on that, and now he's like, it's like, I want
Leo,
good things. So when he reaches
cool?
for it, he's basically saying, I like it, give it to me, I want it. So, basic emotional response, get the good, avoid the bad. So he's like, good, I want it, I want it, I want it. He's like gesturing, I want it, give it to me. Okay, so that's positive. And now, of course, you can imagine doing the other side as well.
Leo, this is Cookie Monster.
So Cookie Monster. It's a blue thing.
Can you find Cookie Monster?
So again, this is just verifying that he can perceive Cookie Monster, he knows the label, he knows where it is.
Leo, Cookie Monster is very bad. He's very bad, Leo. Cookie Monster is very, very bad. He's a scary monster. He wants to get your cookies.
So now, okay. So Cookie Monster, no, none of that. None of that.
Oh, it's okay, Leo.
Okay, now you can
It's
take
okay
these
now.
away. You can show these are actual memories now, and that when you bring these things back, he still has the affective reaction to them. So this is a form of sort of affective, a simple form of affective memory. So I want the yellow thing. I want it. I want it. I want it. And you bring back the Cookie Monster thing, and he's like, no, I don't want that thing. Get it away. So again, you know, a very early, very important form of social learning that we take for granted, but is really critical, especially as you can imagine, infants in the complexity of the human environment with so many things that you don't know if it's safe or dangerous. This is just a fundamental way of learning about the world with and from others. So if you keep pushing that idea now, we've talked about this sort of empathetic, more experiential process by which the robot's trying to coordinate its internal states with you. You can push that beyond affect to look at other cognitive states, such as belief states or goal states. So again, this is inspired by psychology, which basically says, there's this theory called simulation theory, which says one way, one strategy that we have of understanding these other mental states of others is that we basically use ourselves as a simulator for them, saying, if I were perceiving the world from your vantage point, if I were doing those actions in that context, what would I be? What would my goals be? What would my motives be? And that's a starting point for inferring that that might be what the other person might be motivated, what their goals might be. And so it's a notion of this dual use, again, of our cognitive system, not only to generate our own behavior, but then to simulate and infer the behavior of others, the internal states of others. And Andrew Meltzoff hypothesizes that we learn to simulate others through imitation. So this is kind of this evolving story. So if you know, there's a very rich literature now in neuroscience, especially, you know, social neuroscience, looking at, you know, fMRI scans of human brains, where you have people do tasks such as read a story, where they're asked to take their own perspective in the story or the perspective of another, and finding that very similar brain regions are active when you're taking your own perspective versus when you're asked to take the perspective of another person. So again, there's an idea of reuse and sharing of representations. So I'm going to show another video of Leo doing this sort of process in a collaborative task.
Actions are based on incorrect information. Leo keeps track of objects in his environment based on data from his sensors. At the same time, Leo also models the individual perspectives of his human partners. Here, everyone watches as Jesse places cookies.
So those markers on the people's heads are basically a way that Leo has of tracking head pose and hand positions, the state of the boxes and the state of the food items, the chips and cookies. So this is just talking about the cognitive architecture. You can imagine, you know, human brains have all these systems that are interacting with one another. We're trying to model that essentially within the robot.
In this demonstration, Leo tracks sensory data from an optical motion capture
So
system.
Leo is using this Vicon
This same
system to
data is
track
presented to
all of these
different
moving
systems, which
entities and is
represent the unique
essentially
visual
trying to model those into belief states in terms of who's seeing what, who's doing what, where are the state of the objects, where are the locations.
Now, as Matt
So those are the
leaves
belief
room,
states.
Jesse decides to play a trick on him.
Now, this is a
Switches
manipulation
the
based on a
location
classic
of
psychological task called the false belief task that's used to probe children's
Since Matt
developing
is
theory of
absent,
other
Leo
minds,
only updates his
which is
model
when one
of Jesse's
person's gone,
beliefs.
there's a trick that's played on him, which is to switch the objects. So Jesse has seen something, Jesse's the one in red, that Matt is not privy to. So Jesse's beliefs should be different than those of Matt's beliefs. And Leo has seen the trick, so Leo also should be privy to this information.
Now Jesse seals the boxes with
So he's
combination
going to seal the
locks,
boxes. So
preventing
Leo
access
is going to be
to
helpful. You're going to come back and you want either chips or cookies, and Leo has to infer from your actions what, and your belief states, what the desired food item is. And then Leo has a little control box over here that he can operate to open one of two food boxes
When
here
Matt
to help you
returns,
get what you want, because
hungry
you've
for a
locked the
bag of
boxes,
chips,
so it's hard for you to get what
He
you want.
tries to guess the combinations of
So
the
this is a
locks while he
collaborative
remembers
task.
seeing the chips.
So Matt comes back again.
As
Of course, he
Leo
didn't see
watches
what
Matt
happened.
reaching for the lock, he tries to
He's
infer
going for
Matt's
this box,
intention
but
by
we all
switching
know,
from
except for Matt, that the
activities
wrong
that
thing is
matches
in
the
there.
Observed motion and task context. Once a matching activity is found, Leo uses his model of Matt's beliefs to predict what Matt's goal might be. Then, Leo uses his own model of the true state of the world to search for a way to help Matt achieve his goal.
So this is called metacognition. This is thinking about thinking.
Matt's intention, Leo
Now,
assists
even
him
though
by
Matt
helping
has
him
false
connect
beliefs
to
and
the
invalid
intent,
plans, so to speak,
providing
Leo
Matt with
understands
tips
what
he
his true
desires.
intention is and is going to operate this control panel to get Matt what he actually wants, even though he's going for the completely wrong box. So there's the chips.
Thanks, Leo.
All right. And now Jesse comes back.
Now Jesse returns and tries to open the same box.
And of course, he does the exact same actions,
Leo correctly infers that
but he has
Jesse
different
wants
belief
the
states, and Leo
cookies,
understands
since
that.
Jesse is aware of the actual contents of the boxes. Matt and Jesse both perform the same physical action, but Leo's ability to model their individual beliefs allows him to correctly assist them in achieving their different goals.
So Jesse wants the cookies. All right, yay, Leo, okay. So that's all I want to talk about now about social attentions. Of course, you can imagine extending those ideas and pushing them in more complicated situations and other kind of mental states. But now I want to look at a different question, which is the tutelage and learning question.